mind using the mic? Because we actually are recording. Oh, okay, all right.
Yeah. And we need a mic.
Okay. Yeah, I tend to walk around a lot, so.
That's fine. I'll just turn the mic on.
Now I have to juggle the mic and the pointer, so hopefully I won't be pointing the laser pointer in my eye, for example. That'd be bad. And I should talk really quietly now. I'm not used to that. I like shouting. All right, so we're going to have continuous design variables. So the idea is that instead of assigning a distribution, like a normal or uniform distribution to the variables, we're basically saying that we are going to deterministically set the points, set the parameters. All right, so the initial point, the final point, and the number of steps between them. All right, that defines our vector parameter study. Now this is a really simple example because I'm using a built-in function. So the Dakota executable comes with this Rosenbrock function built in. So whereas, in the previous slide I mentioned the analysis driver is a really difficult thing, well, for this example it's very simple because it's already built into Dakota. All right, now for each iteration, I'm going to produce an objective function. So this is the cost function that we seek to minimize. All right, so this is one example of a response from Dakota. You can also just get information back. So this is to Irina's question about, is there any information passed between the different iterations? So in this case, yes. We'll be keeping track of what the minimum value is. In my other examples, I won't be doing that, just so you know. It's possible, but I don't have that set up. I hate using a mic. This is difficult. Okay, so let's try that. Okay. Oh, this is pain. Thank you. Okay, so I want to run Dakota now. This is how it works. Here's the syntax. So Dakota, and you can do this with me if you want. Try this on Beach. Oh, wait, I have an idea. Before you do that. All right, so here's the problem. So Beach is a cluster computer. When we log in, we are on the head node. Okay, so all of us have logged in. A bunch of people in the North Bay have logged in. People upstairs have logged in. So if we run some analysis code on the head node, it's going to bog things down. It would be much better if we could take this and push this off to one of the compute nodes on Beach instead. So I'll try that. Let's see if we can do it. All right. If this bonks, you guys can give me a hard time. But try this. Okay, so this is a little bit off script. So I'm using the qsub command and use the -I flag. Okay, so follow along with this. Or so qsub-I. This puts us on an interactive session on a compute node. All right, so how many compute nodes do we have? Like 70 something? 88 compute nodes. So
It might not be in the path.
Oh.
Or did you set it up to be?
I set up to be in the path.
Oh, yeah.
So qsub should be in your path. If not, if this command does not work, let me know. Okay, so you can see I'm on one of the compute nodes. I'm on compute 4.7. So I'm not low. I'm on Beach. I'm no longer on the head node. This is good because when we do our computations, we won't be bogging down the head node. The problem is that I'm no longer in the directory that I started at. When you log into the head node, it automatically puts you back in your home directory. So let's switch back to the directory where the Dakota input file is. Oh, right, we should, yeah, okay. I'll do that. Yes, we'll do that first. So if I see, yes, so how about this? If you could follow along with me on this. So right now we're back, you can see in your home directory, if you CD into the Dakota tutorial directory and then execute that source statement again, that will set up all your paths. So I'm sourcing scripts setupbeach.sh. And again, if you're on C shell, you need setupbeach.csh. Okay, so now we should have all of our paths. Let's just check to see. Oh, actually, I want Dakota, it's even more important. Cool, all right. Okay, so let's now switch back to that examples directory. So recall, we're in the Dakota tutorial directory. If we cd to examples 1 Rosenbrock, there's our Dakota input file. Okay, let's run Dakota. Here's the syntax. It's really simple. Okay, so I'm calling Dakota, and with the -I flag, I'm specifying my input file. With the -O flag, I'm specifying my output file. So the input file already exists. The output file will be created by Dakota. Okay, hit return. And it goes really quickly because it's a built-in library. Let's take a look at the results. So you can see Dakota has produced a .dat file, that's our tabular data file. It has produced an output file, which is a record of all the iterations of Dakota, and something called a restart file, if you don't need to worry about that. I am particularly interested in the .dat file. Let's take a glance at that. So you can see that it went through 11 iterations. And the reason why is because I specified 10 points, and it does think of them as steps. It does 10 steps starting from the start point. All right, so you can see it goes from along the 2 variables that are defined, from the start point, which we define in the input file, to the end point, defined in the input file. And then the objective function, these are the values of the Rosenbrock function at those points. So this is where does it achieve its minimum? We can look at the output file for that. All right, so the output file tells us that it found the minimum value at the final point. So this is a quick example of running Dakota from the command line. Any questions or comments? I'd like to go a little bit further. Well, yeah, I'll skip that. I have Python notebook where we can go through some quick analysis as well. I think I'll skip it for this one just to save some time. And we'll do that in the next example. Okay, any questions, any comments on this first example? Okay, again, the purpose is just to see what the con syntax is, as well as the syntax of the input, output, and data files. All right. Let's try a more real-world example. All right, so in the second example, I'd again like to use Dakota at the command line, and I want to call HydroTrend. And I'm curious to look at the response of HydroTrend to varying 2 parameters, temperature and precipitation. And I'm going to look at the suspended sediment load. All right, so the purpose of this example is to show the analysis diagram. All right, so again, remember this, I mentioned this is kind of where a lot of complicated work takes place. And I want to show you an example of how an analysis diagram can be written. All right, and the method I'll choose in this case is a multi-dim parameter set. So you can see the hydrotrend Hubert model, Bogart model. I like Hubert better, like Eric. So the suspended sediment load, you can see has a dependency on precipitation through discharge and dependency on temperature. Okay. So I'm back here on my compute node on Beach, and I want to move now up and into the second example, the hydrotrend example. Oops, you can actually CD to do that. Right, so let me take a moment to show you the contents of the input file, and you can see how it differs from our first example. And then we'll take a look at the analysis driver. So this is a Python script. I've chosen to write it as a Python script. We'll look at the input file first. Oops. Oh, my bad. Okay. What I'll do, so you can see I don't have Emacs installed correctly on the compute node. So what I'll do is I'm going to open up another terminal session and get there from here. Sorry about that. And it may be, I have a custom Emacs, so that may be something to do with it. VI probably would have worked. I deserve that. Okay. All right. Okay. So here is our Dakota input file for the second example. You can see again I've defined the name for the, I'm instructing Dakota to make a tag reference file, and I've got its name as well. In this case, we're not going to do a vector parameter study. We're going to do a multi-dim parameter study. And we're going to partition the parameter space, well, actually into a 5 by 5 set of nodes. So there are 4 partitions, which means 5 evaluation nodes per dimension. Okay, so I am specifying the 2 variables, temperature and pressure, and I give lower and upper bounds for each. So temperature will range from 10 to 20, and that's going to be in degrees Celsius. Precipitation will range from 1.5 to 2.5 meters. Okay, so far this isn't very different than what we saw in the previous example. What's next will be different. So whereas in the previous example, this interface section was really small. It just said use the direct interface and call Rosenbrock. Here, I'm using the fork interface. This is what we would use whenever you want to call something that wasn't built into Dakota. I'm specifying the name of my analysis driver and the names of the parameters and results file that are used by Dakota. So, as I suggested, there's going to be 5 by 5, so there's going to be 25 total iterations. Each time through Dakota will call hydrotrend and save the output in a directory called run, and it will save that directory, as well as save the files that it uses. So these are all keywords that are documented in the Dakota API. For output, we'll look at two items. So instead of objective functions, I'm just getting the output from Dakota. Okay, I'm going to get the mean sediment load and then the standard deviation. That's over the simulation time of the model. All right, so this is the input file. It's a little more complicated than the first example. In particular, the analysis driver. Let's look at that next. That's the run hydrotrend script. I won't go into great detail here. Let me try to give an overview, a high-level overview. So basically in this analysis driver, this Python script, I need to tell Dakota where to find hydrotrend's input file or input directory, as well as input files, and also where to locate its output directory, and what file I want to pull out of its output directory. So this goes back to a question earlier. You know, are we using the BMI in this case? No. I'm using the hydrotrend executable that's installed on H. All right, so I'm telling Dakota where, giving it paths where to find information for hydrotrend. I'm calling a built-in routine from Dakota. I'm not sure how to pronounce that, dprepro. And what it does is it makes a hydrotrend input file for me. So the idea is that I have a bunch of hydrotrend parameters, but I want to vary two of them, temperature and precipitation. So I start with a template for my hydrotrend input file. So I have a bunch of default values that I'll use, but you can see every time through, so for each iteration, Dakota will replace these T and P variables in the hydrotrend input file with its values from its parameters file. So that is done by this dprepro script. All right, so for each time through, I set up a new hydrotrend input file. I then call hydrotrend and parse the output. So in this case, what I've done is I've taken the QS file from hydrotrend and I compute the mean and standard deviation. And I give those back to Dakota. I write the Dakota responses file. Okay, so I know that's a bit of information, but I wanted to show it to you just because this shows kind of the difficulty in writing an analysis driver for Dakota. And this is the thing that I hope I've extracted away in the Python interface and the WMT interface. Yep, go ahead.
What happens if the input file is got the curly brackets?
That's a good question. You can escape that. So with a slash. The dprepro command will understand a backslash curly brace, and that will escape it. Good question, though. Okay, other questions or comments? Okay, let's run this example and then look at the output in an IPython notebook. Okay, so here I am back in my terminal window that actually has, it's on my compute node. And I want to call Dakota. So the same syntax. So Dakota-I, the input file, -O, I'll make a new output file. Okay, so hydrotrend's been run 25 times now. When I see it's running. compute node. So this would be a lot faster than if we run that node. If I were smarter inside of my analysis driver, I would put something like a counter. Think about that right there.
How many cores do these compute like that?
What's that?
How many cores do they
8.
compute?
I'm using one.
Can you run them?
I could use either more cores. So Dakota, for example, has a couple different levels of parallelism. So you could, for example, set things up through MPI. It understands that. It also has something that it calls interparallelism. So it's using one processor for putting jobs on different threads. As long as they don't talk to each other. I could use that here, for example. That would be great. I could use one processor because they're all independent. Yeah, that's kind of neat. Is that thunder? Oh, wow, okay. All right, cool. Let's take a look at the results. All right, so you can see there's all the Dakota runs, so all 25 of them. All right, you can see we also have, I usually have a pocket in my shirt where I can put things. I don't have a pocket. I feel a little lost. All right, so we've got our output file, we've got our data file, and all those runs. Let's take a look at the data file. All right. So you can see that we just stepped through over temperature and precipitation, and then calculated the mean QS and standard deviation for each parameter value. All right, so in a tabular form, yeah, okay, I can kind of see information. It'd be much better if we had this in a graphical form. So I have some IPython notebooks. Let's try those, because that'll be fun. All right, I'm trying to think of the best way to do this. How about this? So I have some instructions, and I'll put them up on the screen to make it easier to look at. So, okay. So this is this earlier slide. We have the tutorial. I have that up already. All right. So you can see I've got those notebooks. You can't. An IPython notebook is just a JSON file. So looking at it in its raw form is not very helpful. So one way to look at them in a static way, you can either look at them through GitHub, which is kind of handy. I can go to notebooks, and there's one here, how to start IPython. That font is really small, isn't it? How is this? Can you guys in the back see this? See this okay? I can make the font bigger otherwise. All right. So the idea is, I know that even though you may have an IPython notebook installed locally in your laptops, all of the data that we're working with are on Beach. So obviously you could either transfer data from Beach over your local laptops, but you could instead just run IPython notebook from Beach, and that's what these instructions are for. And this is Eric helped me with this. I tested it with Dakota. So what I'll do, and do along with you, is so I've already SSH. Well, I can SSH in a different terminal, and then call IPython notebook. Okay, but call IPython notebook with no browser flag set, so that it'll just run in the background. And optionally, yes, optionally you can background the process as well. Okay, so this could be from your local machine. This is on Beach. All right, and you'll see that IPython notebook will run, and it'll tell you what port it's running on. We're then going to SSH again into Beach in order to get that port, and then we can run the IPython notebook locally on our machine. Okay, so these instructions, you guys can keep these up, for example, on your web browser. I'm going to go to my terminal window and start entering this code. So I can run an IPython notebook.
Mark, they just source your setup file to get IPython in the path.
Oh, how about this? If you use the same, if you skip this step, because we've already done this, if you just use the same session that you've already used, and then background the process, then you'll have that source. Otherwise, yeah, after the SSH step, go in and source the setup script again. Thank you, Eric. Okay, so I'm entering the IPython notebook, no browser. I'll background it. Oh, that's because I forgot to do that. Oh, rats. I forgot to source on this one. Okay, so I executed IPython notebook, no browser. I backgrounded the process, so I still have access to the shell prompt. You can see IPython said all these ports are busy, and I'm running on localhost 8886. So I have to remember that number for a while. Oh. Don't try them.
Well, then you have to forward the port.
Oh, no, not the IPython notebook. Yes,
Oh,
the
yeah.
IPython notebook will do from the head node still. Yeah. Okay, so the next step then. Okay. You can see I tried this earlier. And what was it? 8886 is mine. 8886. Okay, so this is mine. Yours may be different if you're trying your own.
That's a major one.
Now, unfortunately, this does not give me any feedback at all. I wish it would do something, but what I can do is go to my web browser now and try this. So the URL is, HTTP, not HTTPS, localhost, colon, then that number that you got. Now you can see I was playing with this earlier. Right, and there's my Dakota directory. Okay, let me know if I can help with any of these steps. Yes. Do you want to see this one or the other one? Okay. And again, remember, this slide is in your, is on my GitHub repository, so you can go there and look there as well. If anyone else is having issues, Eric will be able to help. Okay. So I'd like to experiment with the IPython notebook to look at the results of this experiment. Okay, so I started IPython notebook from my Dakota tutorial. I can go into notebooks, and you can see that there are a bunch of IPython notebooks. Maybe the easiest is just to go to the HydroTrend one. All right, so here's the IPython notebook for the second experiment. What I think is fun about IPython notebooks is that I can mix text with code. And so it tells a story. It's sort of an interactive story. All right. So the first command is a setup command. I'm going to use Pylab inline. This allows me to display figures on the web page. All right, so the way that we can navigate an IPython notebook is, you can see I put my cursor into this code box. I can hit Control-Enter or Shift-Enter. Control-Enter executes the code and stays in the box. If you do Shift-Enter, it will advance. So I'll do Shift-Enter. Okay? So you can see that the IPython notebook says it executed that first statement, and when calling this Pylab magic function, I got a note back saying it's all good. All right, let's continue. All right, so I want to read in that Dakota tabular data file. So this is maybe a little sloppy, but I'm using a relative path to go into the examples HydroTrend directory and get that data file that we just created. I'll then read it in with a NumPy routine, the NumPy load text routine, which is really nice for reading tabular data. All right, so I can do Shift-Enter. All right, so now I want to pull out, actually, gosh, maybe I should look at that data. How would I do this? I can insert a new cell and let me do something like this. Let's say if I just type data, all right, you can see I get an output. That's all the data I've read in. Or say, for example, I want to get a shape. Okay, so 5 columns by 25 values. And I skipped the first row because that was the header. And I also skipped column number 1. That was the one that had text in it. It said empty, 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 empty. Okay, so next, let's pull out the temperature and precipitation parameter values from that tabular data array. Okay, so the temperature values were in column 1, and we start counting at 0, and the precipitation parameter values were in column 2. Okay, so there are my temperature and precipitation values. You can verify by eye that they match up with the Dakota data file. Now next, just because I think it's useful, let's visualize the parameter space that we're using and the points in parameter space where we are evaluating HydroTrend. All right, so you can see the 5 by 5 grid of nodes where we evaluate HydroTrend. And this is, I know that the font is a little small, but that's temperature along the horizontal axis and precipitation along the vertical axis. Okay, so this is where we made HydroTrend runs. Next, let's do some visualization of the output. Okay, so I want to use the Axes 3D package that's in Matplotlib, and to do that, I need to reshape the arrays for temperature and precipitation. So, because right now, temperature and precipitation are these one-dimensional vectors. I need to reshape them into two-dimensional arrays. Okay, so I reshape temperature, precipitation, and Q sub S. And actually, let's just take a look at that. If I do QS shape. Oops. There. Okay, so it's a 5x5 array now. All right, let's make a wire mesh surface plot then. Okay, and this is again using the Matplotlib, the Access 3D package. All right, so oops. Yeah, okay. So temperature, precipitation, and Q sub S. You can see this isn't terribly exciting. Over these range of parameter values, I have a pretty flat response. Well, not flat, so the derivative is not is zero. Right, we're not doing anything. Well, the second derivative is zero. And just to show you, you can also make a contour plot. I didn't put a key on this contour plot, but temperature, precipitation, and then increasing values of Q sub S are lighter shading. It would have been better if I put a key there, but okay, so this is an example of using IPython Notebook to visualize the output. I think it's kind of fun. Any questions or comments? So, two more items to cover. And I realize I'm talking a little too much. I need to stop talking and show you that. So, the next thing we're going to look at okay, we just did example 2. So, the next thing we're going to look at is Dakota in Python. So, currently we're running some wrappers for Dakota in Python. Right, and so why? Well, because we want to set up simplify the setup of Dakota experiments. You saw that analysis driver in the second example, that was a bit of code there. Right? If I could somehow abstract that away, it would make it easier for us to use Dakota to actually do some science, as opposed to worry about all the coding. Right, and this will also then be a first step for writing a BMI for Dakota. Right, so. This is under active development. You can see it has a very high release number. And we have all the code up on GitHub as well. So you can take a look at it. All right, so some of the features of this package. It writes a Dakota input file for you, so you don't have to do that. It also implements a generic analysis driver. So you don't have to do that either. So that was kind of a pain. And third, it communicates with Dakota through an auxiliary configuration file. The neat thing about that is if you set up an experiment with this configuration file, you can take that configuration file and use it in another experiment. You can tweak the values a little bit. And so it's really easy to make a portable experiment using this package. Right, so those are the positive aspects. There are some negative aspects of what I've done so far as well. Okay, so I've only done these 3 parameter studies. We saw in an earlier slide that there are dozens of Dakota analysis methods available. So I've only wrapped 3 of them. There's much more to be done. I've only worked with hydrotrends so far. In the CSDMS we have hundreds of over 200 models. So I've only worked with hydrotrends so far. The responses are restricted to basic NumPy statistics, so things like mean, standard deviation, median, range, things like that. And currently it's not coupleable, so I'm not using a BMI. I'm using the BMI version of hydrogen. All right, so there are some positive and negative aspects to this package. Here's the basic calling syntax for this package. So if you're in Python, you can import this Dakota class. You can set up a Dakota instance and tell it what analysis method to use. So vector parameter study, descendant parameter study, or multi-dim parameter study. You can then change settings, write a configuration file, write an output file, and then run Dakota. Oops. Okay, so I'd like to show an example of this. All right, so in this example, it'll be similar to the previous example, and now we're going to be calling hydrotrend. We're going to look at some different parameters though. So mean river velocity and the constant annual base flow. And we're going to see how it affects the median daily deadlift values. All right, the purpose of this example then is to show how to configure on Dakota through the Python interface. And we'll use the center parameter study for this. So for this one, because I'm using Python, we can actually go through an IPython notebook. All right, so here's my list of IPython notebooks that I have running on, well, my list of IPython notebooks. One of them is running on Beach. I should turn that one off. There we go. And we can use this third one. Okay, so I can now call Dakota from this IPython notebook. All right, so again, let me just go through this. If you have any questions as we go through, please let me know. You can also do this as well on your IPython notebook if you have it set up. All right, so Pylab Magic. I have a couple other imports that I'll use later. Okay, with the first step, I want to import my Dakota class. And then next I can create a new Dakota instance of a centered parameter study. I make a note here that the method name matches the syntax of the Dakota keywords. So you can look at the Dakota help page to see the syntax of this particular keyword. Okay, so I now have a Dakota instance. You can see that this Dakota instance has a couple attributes that are already defined. So it defines the input file and the output file for the Dakota run. It also defines a method object. All right, and this is going to be, it'll contain other attributes that are used for a centered parameter study. So what I want to do next is configure this method object for this centered parameter study. So I'm going to pull it out, and you can see all of its attributes. So a lot of these names look similar to the keywords that you saw in the Dakota input file. All right, so you can see there's also a lot of default values. Basically, I use the Rosenbrock, where'd it go? As my default. Okay, so we need to override these default parameter values. All right, so I want to tell this method object that we're going to run on Hydrotrend using the fork interface, and our run directory will be this directory inside of our project. And again, recall that fork interface is what is used when we call something outside of Dakota. Okay, so again, we're varying mean river velocity and constant annual base flow. All the other parameters in hydrotrend will be held at a constant. Okay, so I'm using the standard names that we set up for these two variables. These are found in the hydrotrend input file. I'm setting up initial point. So this is again similar to what we saw in the Dakota input file for the other two examples. I have an input point. I have a step vector. So this is going to be the step size in each dimension and parameter space, and the steps per variable. So, and this is in each direction. So this means that mean river velocity is centered at 1 and has 3 steps in each direction with a step size of 0.2, so a total of 7 steps for river mean velocity and a total of 5 steps for base flow. That was a little tricky. Okay.
Can you say that again?
Yeah, so sorry about that. So river mean velocity, so this is a centered parameter space, so we can cross in parameter space. And mean river velocity is centered at 0 at 1 and has 3 steps on either side of that center point. Yep, exactly. Okay. All right, so I've defined a little helper function that will set up these points. That's one fun thing about IPython Notebook is I can write a little routine right inside of it. And then I'll use that routine. So although this is tabular, maybe it makes any more sense now. So for the mean river velocity, centered at 1, 3 points on either side. For the constant base flow, centered at 1, 2 points on either side. And because it's never enough to have just tabular information, we have to make a plot. So a quick plot to show these parameters. Again, this is constant base, this is river velocity and the constant annual base flow. All right, so we know where we're going to evaluate hydrotrend. Let's tell Dakota what information we want to get out of each hydrotrend run. Okay, so I want to get the median value, in this case, out of each of the QB files. There's a bunch of configuration here. We're almost done. All right, hydrotrend also requires a hypsometry file, so I'll tell Dakota where to find that. All right, so recall in the previous example, we had a template file that we provided to Dakota. So hydrotrend has an input file that has all of its values. The template file has all those input values except for those 2, well, in this case, the 2 parameters that were varying. And those are replaced with variables with curly braces. That's what's being set up here. All right, so I'm saying where it is. And I'm going to use a static method from the hydrotrend class in order to actually make that file. So that makes my template file. Okay, almost done. The last step, and recall this is one that was kind of hard earlier, the analysis driver has already been written for you. All right, so this is done within this Dakota package. We just need to tell Dakota what it is. Okay, so if I look at all of the attributes of my method object, you can see I've got stuff all set up. So all this information I can use to describe my experiment to Dakota. All right, so I'm going to take this information and dump it off to a configuration file. All right, so I'm going to change to my run directory and then write the configuration file. All right, I'll write the input file. And before I run Dakota, let me go check really quickly if everything's there. All right, so this is that directory 3-Python. Okay, good. So we've got our configuration file. We've got our Dakota input file. It's all good. Our hexometry file. Our template file. All good. So, for example, we could run Dakota from the command line here, but instead, we'll run Dakota from Python. Now, that may take a little bit, because this isn't running on the head. This may take a little bit longer, and we're going to be, 7 plus 5, 12 iterations. And you can see there's a little asterisk, so it's running.
Paul was running a question about the template file. Yeah. You put the curly brackets with the P in there.
Yep.
That's fine if the file, I assume if you've got a formatted file, just almost specify how many spaces that takes up and all sorts of little file.
Question. Yes, that's a good question. So this is all based on the Pro script that's provided. So it's a convenience. You could write your own script in order to replace template values, parameter values. I think that the prepper does a nice job of honoring spaces because I've used that actually in several places in hydrogen parameters. Because some of the hydrogen input parameters are tab or space separated. So it seems to work. But recognize that I am relying upon third-party software to take care of that. If I want to be really careful, I can make my own.
I'm thinking of really old Fortran keys, columns.
Exactly. Everything. Yes. Hey, okay, so it's finished. Let's take a look. Well, let's take a look quickly. Oh no, I can do this in Python. Why use the shell when I have Python? All right, so in IPython, you can see I can get a directory listing. This is the ls magic. Hey, look at that. So we got all of our runs there. There's our dakota.dat file. Let's take a look at that dakota.dat file. Some more magic. There we go. So there's our iterations. You can see the two parameters that we varied as well as the output. Okay, so we can read these data in. Again, I'll use the NumPy load text function and make a plot. There we go. So this again is that's mean river speed, and this is the constant base flow. So not super exciting, but just a demonstration at least of how we can use this these Python wrappers. Okay, questions or comments? Go ahead.
So I came in late, but so far it looks like Dakota isn't doing anything you couldn't do in a JavaScript that submitted a bunch of files.
I absolutely agree. And this is because of just what I have done. There's much more that can be done with Dakota. I started with these very simple techniques that are available in Dakota. So I absolutely agree. This could all be done by yourself. I think what the advantage to using Dakota is that once you understand how it works, then you can go on and use more advanced techniques. And instead of writing them yourself in the script, for example. But I absolutely agree. What I've shown so far does not really do justice to what you can do with Dakota.
Yeah, so we did work where we're having GA and tech GA, and it's essentially the same thing. So once you know how to do this, it's very simple, very straightforward.
Yep.
We were using Untitled Chapter.
That's totally good to hear. Because I'll be doing that as well. Okay. All right, oops. Okay, so the last topic I have in this clinic. Okay, we gotta go 3:30. 3:30, okay. I'm trying to get done a little early, so it'll be a little bit early. I don't have first talk yet. All right, so the big goal of this is try to get Dakota running in WMT. Okay, so we're currently working on that. And we have a development prototype. And it works, but it's limited. Okay, so it's limited in the same way that I've described the limitations of the Python wrappers because I'm using the Python wrappers underneath. All right, so it's limited to only these 3 parameter studies that I've written so far. It uses only hydrotrend. Again, partly because I'm not using the BMI. Once I figure out how to wrap a BMI model with Dakota, it'll go a lot faster to get other models here as well. So I've limited the responses to NumPy calculations. And again, it's not couplable. I'm using the hydrotrend on Beach as executable, not as the BMI version of hydrotrend. All right, but we can try it. Click on this link. Oh, actually, do I have another? Yeah, I don't. Okay, so click on the link. There we go. Okay, so if you have not used WMT before, it asks you for an email and a password to log in. Now, this is not your email and password that you use on the system's website. That I'm going to fix this summer so that you have the same login. But for right now, you can just put in any email address, hopefully one that you own, and a password. My test is foo@bar.com, so, but I'll use my one that I've been using. Okay, so it tries to remember, you can see. All right, so if you've never used WMT before, you can enter an email address and a password. You'll be prompted to repeat your password and remember it, write it down, and then you'll be able to use WMT. How many people have not seen WMT before? Okay, so a few people. Let me take just a few minutes to talk about how it works. All right, so you can open existing models, and I'll do that in a moment. All right, what's kind of fun is that you can build your own simulations from coupleable components. Now again, unfortunately, I have not got Dakota coupled yet, but that's the overall idea in WMT. So I can select what kind of Dakota job I want to do. All right, and you can see this is a special version of WMT. And then it doesn't include a bunch of the other components. I've got that special URL here. Okay, so for example, if I wanted to do a vector parameter study, I could choose then what component I want to use, which hydrotrend is the only choice. All right, so I'm trying to do a vector parameter study with hydrotrend. You can see on the right panel, the parameters for the vector parameter study are shown. And you can enter values. So I've got a default here, 4 steps along the vector, and a default parameter that I'll look at, and a default output. If you click the little arrow, so you can see if you, well, I worry that this is not a user-friendly way, but you can, if you click the arrow, you can see you can set additional parameters as well.
Mark, people are getting the error messages. They're trying to get people into your Dakota.
looking at it. But yeah, be sure to use HTTPS, not HTTP. Okay, yeah. Okay, so this is a quick. Oh, I guess I can show a couple more things. So you can configure a simulation. You can save it. You can run it. There's also some additional attributes you can attach to a simulation, like you can have labels that you can use to find it at a later point. You can then search by label when you open. Over in the parameters, you can see, for example, what the input file would look like. Now, that's not quite as useful, but for HydroTrend, you can see, aha, there's a HydroTrend input file. All right, so this is the kind of thing you can do with WMT. All right, so in the last example, so I want to use WMT to do something very similar to what I did in the second example. So looking at temperature and precipitation on suspended sediment load. This is going to be a multi-dim parameter study. And the purpose of this example is to show how I could do that through WMT and how much less work there is. All right, so I have a couple examples. The example that I have up on the slide is one where I partitioned the space. So what we did a 4x4 partition in the other example. I did 40 by 30 in my example. So there's a total of over 1,200 calls to HydroTrend, which is kind of fun. It took like half an hour to run, so maybe we won't do that one. But we can try a smaller one, for example. So if you'd like, you can go to WMT. I'm going to clear out this, what I've done. And if you open, okay, so you get an open model dialog. For most of you, it'll be empty. But if you click on the labels button, and then click the public button, the list should be populated with some models. Okay, so look for public. All right. So you can see I have a series of saved parameter studies. I think the one that I would like to use here, because it shouldn't take too long, is multi-dim parameter study MP1. Let me know if you can't see that.
The labels have to unclick there.
Yes, yeah. So yeah. Thank you, Eric. So under the labels, unclick your username and click the public label. That way, it'll show all publicly available models that are not associated with your username. Okay, so I've loaded in that saved model. This is multi-dim parameter study MP1. All right. So there's my starting temperature and precipitation, and then my output. All right, so this is a 10 by 10. It'll still take a little bit of time. Maybe I'll change that. Well, yeah, we should change that. So I'm going to make that a little bit less. I'll do it 5 by 5, just because I don't want to take too much time with this. Okay, so I've modified those parameters, and you'll see now there's a little asterisk next to the file name. Now, because this is a public model, guys can't save it with the same name. So instead of clicking the save icon, go to the more menu, oops, and do a save as. And it'll prompt you with the default name of the name copy. And that'll be fine. And maybe don't make it public either. Unless everyone can see it, it's not a big deal. Okay, so this would be a copy. Right. Or you can even see entirely different. Okay, so I've changed the number of partitions. This will reduce the number of Hypertrain runs to a quicker number. A number they'll execute. All right, so after I've saved it, I can now run this. Well, I call it a model, but we'll execute Dakota. So I'm going to click on the run icon. And this is where you need to know your Beach login and password again, because this will run on Beach. All right, so I'll put in mine. Okay, then I'll select run. Okay, and you can see you get a little message saying that your model run has been submitted. I can look at it by clicking that run status button. And I can see other people are running as well. Oh, there's me. I think this is me right here. All right, so some of them will work, some of them haven't. I see there are a couple that didn't work. I'm just hitting refresh. Sometimes. Okay, so if your run didn't work, either try it again, or if you like, you can just grab the output from mine as well, or from one of these that did work. All right, so like this one's mine. It says okay. I can download it by clicking the little download. Now, I think what I want to do is something a little different. So if we click the download icon, this is on my web browser on my local machine, it'll download the data to my laptop. I want to use it on Beach instead. All right, so if you like, please, if you like, follow me with this. If I put my cursor over that download icon, I get the path that's actually being used. So if I right click, I could actually copy that link. All right, so again, you could download this locally on your machine and then rsync it back to Beach. That would also work. I'm providing another way that may be a little bit easier. Okay, I have a last IPython notebook. So there's IPython Notebook 4. All right, so I want to download the model output from WMT and examine the results. All right, so first of all, take care of the setup. All right, I'm going to change to the directory where I can process the output. Okay, now this is the point where, if you'd like, you can try to put in the output from the runs that we've just done here. So I've hard-coded in here another run. That was the big 40 by 30 run. And you can see that it has a run ID. And we can pull that run ID off of the link, the download link that we saw on the WMT page. to try that. So let me just paste that link in here. Okay, what I'm interested in is this big UUID from the link. All right, so I'm going to grab that and paste it in here. There. I know this is not the most elegant way to go about this, but it's also operating system neutral. I can do all this in my IPython notebook. So this is the run that I just completed. I can edit that here too. There, that's what I just did. Okay, so let's try to download it. All right, so obviously you could use like wget and tar to get this file and unpack it, but here is a pure Python solution. We don't have to go to the shell. Okay, and so here's the call to that function. Let's see if it did the right job. So I'm going to change to my run directory and do an ls. Good deal, yeah. Okay, so you can see this is kind of the standard packaging for a WMT run. There's a couple YAML files that provide descriptions, and all the information is inside that multi-dim parameter study directory. So let's change to that directory. And actually, let's do an ls. So I'm going to insert another cell and do the ls magic. There. So you can see that inside that parameter study directory are all the subdirectories created by Dakota, as well as our dakota.dat file, our dakota.in file, dakota.out file. Let's read the Dakota.dat file. And you can see I put a little extra information on what's the shape of the data. Okay, 36 runs. Okay, so this is a multi-dim parameter study. So recall I want to try to make some surface plots. I need to reshape the data. And I can make my surface plot. Ta-da! This is an example of using Dakota in WMT and looking at the output. Any questions, any comments? All right. Yep, go for it. Yep.
One question that Don will ask is what does Dakota do if one of those runs dies or goes into
Good question. Yes. So there are ways to trap errors in Dakota. So there is an error handling mechanism in Dakota. It's pretty simple actually. You can just basically pass null outputs to the Dakota.out file. Actually, you can use NAND as well to protect your data. So Dakota has some simple error for one thing. Okay, so that's it. So I have a quick summary. All right, so we have developed prototype Dakota interfaces for Python and for WMT. And as I mentioned, they have some drawbacks. They're only prototypes still. So only a few analysis methods have been implemented. Only one model is supported. The responses are limited. And these two interfaces are not couplable in the CSDMS framework. On the other hand, they do work and they do make Dakota easier to use. So it's a starting point at least. A starting point for some future work. All right, so what we do next is, first of all, bring these two prototypes into the systems framework. I think that will make things easier afterward. Once I get Dakota to communicate with BMI models, it'll be a lot easier to add other BMI models. So it'll be easier to add, and also lead to faster execution rather than using the file-based Dakota learning. So I want to add more Dakota analysis methods. This is actually pretty easy. I just write basically a class for each. And, as we mentioned, once you've done one, it's not too hard to do others. I need to put up documentation, so if other people want to do this, they can know how to do it as well. And again, I wanted to explore the Dakota library API, because it would work nicely with BMI components. All right, that's it. Thanks, guys, for listening. Any questions? We'll stick around. Yeah, 10 minutes early. So, anyway, here's some time if you want to talk about stuff. I can walk around, talk about stuff.